Section 7.6, Modeling with Trigonometric Functions. In this section, we're going to take a look at how sinusoidal functions can be used to model various phenomena. Recall back from section 6.1, a sinusoidal function is any function in the form of y equals a sine bx minus c plus d, or y equals a cosine bx minus c plus d, where b is a positive number. In the previous section, we talked about how a, b, c, and d told us about different attributes of the wave. The absolute value of a was the amplitude, and the amplitude represented the maximum distance or displacement from rest or the midline of the wave. The phase or horizontal shift represented how far the wave was shifted left or right. D was the vertical shift, which represented the midline, which told us that the midline was y equals d. Now, as far as applications, the midline is often associated with equilibrium or rest or the average value of the function. We also discussed that 2 pi over b was the period, and the period is the amount x changes in order to complete one cycle. If our independent variable is time, one way to interpret the period, it would be the amount of time it would take the wave to complete one cycle. Now, a concept that goes hand in hand with period is the frequency. The frequency is the reciprocal of the period, which would be b over 2 pi. The frequency is the number of cycles that are completed when x changes by 1 unit. If our independent variable is time measured in seconds, the number of cycles completed per second is referred to as a hertz, which we abbreviate as Hz. 1 megahertz is the millions of cycles per second. In this example, the average person's blood pressure is modeled by the function f of t equals 20 sine 8 over 3 pi t plus 100, where f of t represents the blood pressure at time t measured in seconds. Interpret the function in terms of period and frequency. So first, let's figure out the period and the frequency of our equation. If we take a look at our equation, b is 8/3 pi, but period, if you recall from the previous slide, can be calculated using 2 pi over b. So our period would be 2 pi over 8/3, pi's would cancel. 2 divided by 8/3 is the same as 2 times 3/8, which is 3/4. The frequency is b over 2 pi, or the reciprocal of the period. Since our period is 3/4, that means our frequency is 4/3. What are a few of the interpretations of the period and the frequency? Well, the period represents the amount of time it takes for a sinusoidal function to complete one cycle. So in this problem, it would take 0.75 seconds for our blood pressure to complete one cycle. Because the frequency is 4/3, that tells us that 1.33 cycles of this person's blood pressure is complete in 1 second. Further interpretations of the period does also depend on what specifically you're looking at. Perhaps when looking at the blood pressure, perhaps there's certain levels that are considered dangerous. So by knowing the period, you know how much time there is between those dangerous moments. But it does depend on context and what exactly you're looking for in this model. In this problem here, the hour hand of a large clock on the wall in Union Station measures 24 inches in length. At noon, the tip of the hand is 30 inches from the ceiling. At 3 p.m., the tip is 54 inches from the ceiling. At 6 p.m., 78 inches. At 9 p.m., it is again 54 inches from the ceiling. And at midnight, the tip of the hour hand returns to its original position, 30 inches from the ceiling. Let y equal the distance from the tip of the hour hand to the ceiling x hours after noon. And we're going to find the equation that models the motion of the clock. This example is a great example of a phenomenon that occurs in a cycle. We have a clock that has a hand that's rotating on its face. And we know from how clocks work, every 12 hours, the hand is going to return to its original position and go through the motion again. When we're dealing with problems that involve some sort of cyclical motion or some sort of cycle pattern to them, that's when we want to use the sinusoidal function. So our model should be in the form of a sine b of x minus c plus d. From there, we need to figure out what our values of a, b, c, and d are. Now let's think about the pattern they tell us. Recall that x represents the number of hours after noon. So when x equals 0, we know that y equals 30. At 3 p.m., which would be x equals 3, the tip of our hand would be 54 inches from the ceiling, in which case y is 54. At 6 p.m., which is x equals 6, the tip of our hand is 78 inches from the ceiling. At 9 p.m., which is when x equals 9, the tip of our hand is 54 inches from the ceiling. Then at midnight, which is 12 hours after noon, which means x equals 12, our hand returns to the original position where the tip is 30 inches from the ceiling. And we know this cycle would repeat. So what we have done is we've come up with one period of this motion. And we can see from how long this period is, our period is 12 hours, which does make sense since it takes the hour hand 12 hours to make a full revolution around the clock. So with this information, we can now figure out the value of b, because 12 would equal 2 pi over b, which means b is equal to pi over 6. Now that we have b, we have to think a little carefully about how we can figure out the value of c. We know our phase shift is c over b, but if we think about how sine starts in its pattern, sine's pattern is d, a plus d, d, a minus d, and d. A plus d or negative a plus d were the extremes, either the maximum or the minimum value depending on the sign of a. If we look carefully at our table, we see that 78 is our maximum, while 30 is our minimum. Well, according to the pattern of sine, we should start with a value on our midline. So what this tells me is perhaps sine may not necessarily be the best choice. Remember, with sinusoidal functions, we could use sine or we can use cosine. Let's try replacing our sine with cosine, seeing if we can make a better model. Our period is still going to be the same, which means our b is still going to be the same. All that's going to change now is the pattern that we have to think about. Recall that the pattern for cosine is a plus d, negative a plus d, a plus d. Here, the a plus d, the negative a plus d, and the a plus d are the extreme. A plus d would either be a maximum or minimum value, while the negative a plus d would be the opposite, either a minimum or maximum. This seems to coincide nicer with what we have for our pattern. So by comparing the pattern that we have for cosine with the table, two things occur. First, we can see that d equals 54, and two, we can see that a plus d equals 30. Well, with these two, that tells us that a plus 54 equals 30, which means that a is negative 24. So now we've just figured out a and d. And now that we know b, we can figure out c using our phase shift. Recall that the phase shift is c over b. And c over b is where we would start our cycle when we're picking our 5 key points. So here we have that c over b equals 0, since we're starting our cycle here at x equals 0. So c over pi over 6 equals 0, which means c equals 0. If we chose to stick with sine, then we would have to introduce a phase shift, because at that point our period would actually start at 3 instead. Because we decided to switch our function from sine to cosine for convenience, we were able to make c 0, and now we have all the letters we need for our model. And when we plug the values in place, we have y equals negative 24 cosine of pi over 6x plus 54. Next, a Ferris wheel is 25 meters in diameter and boarded from a platform that is 5 meters above the ground. The 6 o'clock position on the Ferris wheel is level with the loading platform. The wheel completes one full revolution in 5 minutes. The function h equals f of t gives the height in meters above the ground t minutes after the Ferris wheel begins to turn. Our task is to write an equation for h equals f of t. Like the last problem, we're trying to model something that is moving in a cycle, since we have a Ferris wheel that is revolving. So for that reason, we should use a sinusoidal function. So like the last problem, we'll start with a sine bx minus c plus d, and if we need to readjust sine to cosine, we can, depending on the pattern that we see fit. Now, one piece of information that jumps out is that the wheel completes one revolution in 5 minutes. What this tells me that the period is 5 minutes, and since t is measured in minutes, we'll keep our period measured in minutes. Recall by definition, the period does represent how long it takes for something to complete one cycle. So we have that 2 pi over b equals 5, where b equals 2 pi over 5. So now we figured out b. And just like in the last problem, if we need to switch the cosine, we can go ahead and switch the cosine and b will stay exactly the same. Now we need to think about the pattern and the various heights throughout the motion. Since our period is 5, and we know we're dealing with a sinusoidal function, if we take our period and divide by 4, that is the difference between the points that are located either on the midline or a maximum or a minimum. To help us understand our pattern, let's draw a picture. The orange line at the bottom is the ground, the blue will be the platform, and we know from the problem, the platform is 5 meters above the ground. We also know that the diameter is 25 meters. Now, what exactly do they mean at the 6 o'clock position? Oftentimes, when people are describing positions of round objects or something in a circle, we can think of the faces of the clock. 6 o'clock would be at the bottom here. So at this red point, that's where we start. So if we think about our pattern for how we would travel a quarter of a period, we would start at 5 meters above the ground, but then a quarter of the period through, we make a quarter of a rotation. So after a quarter of a period, we'll be over at the side. Well, how high above the ground will it be at this side here? Since the diameter is 25 meters, that means the radius is 12.5 meters. Since I want to know how far above the ground this second red point is, I'm looking at the vertical distance from the ground to that point. Well, we can see with the platform and the radii that I drew, I made a rectangle. The vertical side would be 12.5 plus 5, or 17.5 meters above the ground. So after a quarter rotation, or a quarter of our period, we are 17.5 meters above the ground. Then we travel another quarter revolution, and we're going to wind up here at the tippy top. Well, the radius is still 12.5, and from the top of the Ferris wheel to the bottom of the Ferris wheel would be 12.5 plus 12.5, which is the 25-meter diameter, plus the height of the platform. That means at the tippy top, we're 30 meters above the ground. Then we go another quarter rotation, we're off to the side again, which means we return to being 17.5 meters above the ground. Then after another quarter rotation, we wind up right back where we started, 5 meters above the ground. Now if we take a look at our pattern, 5 would be our minimum values, but 30 would be our maximum value. Well, if we think about how cycles of sine versus cosine start, sine starts at the midline, then goes to a max or min, then midline, and so on and so forth. Since I'm starting at a minimum, instead of working with sine, let's use cosine instead. This is going to allow me to make my phase shift 0, because at the start of my motion is when t equals 0. Since we're starting at a minimum or a maximum, our phase shift, c over b would equal 0, which means c equals 0. Now, just like before, the 1.75 would be our d, because of the pattern. D comes second in the pattern for cosine, and a plus d, which is the start of the pattern of cosine, would be 5. So we can solve for a by plugging in the 1.75, and we get a equals negative 12.5. Now we've identified a, b, c, and d, which means our model will be negative 12.5 cosine of 2 pi over 5x plus 17.5. In some problems, we may not have a phenomenon that we're working with that we completely understand the behavior of. So for example, let's say through some sort of experimentation, after taking a measurement of something every second, we were able to come up with this table of data. What we're going to do is try to find the possible formula of a trigonometric function whose values are on the following table, where t is time measured in seconds. Now, how could we tell that a trigonometric function would be best to represent this data? If we take a look very closely at the table, we can see there's an oscillation effect. We're starting at a value 3, then we hit a peak value, then we begin to descend back down to something roughly close to 3, and then we get to descend all the way down to about negative 0.8, and from there we begin to climb back up to something close to 3, then back up to a peak, then we descend down back to a value close to 3, where we end at a value very close to negative 0.8. So this oscillation from going up to down would tell us that we should use a sinusoidal function to represent this phenomenon. Just like in our previous examples, we'll start with y equals a sine of b of x minus c plus d. Depending on what we find convenient, we may switch the sign for cosine later. Now what we're going to do is we're going to try to figure out the value of a, because we can see from the table that the maximum value is 6.8093. Our minimum value is a negative 0.813. And if you recall from previous sections or earlier this section, our amplitude, which is the absolute value of a, equals 1/2 the absolute value, the difference between our maximum and our minimum value. So going to the Desmos, we get that our amplitude is approximately 3.8. So A is either positive 3.8 or negative 3.8. But which one of these two should we use, the positive or the negative? We're going to determine what sign of A we should use the same time we determine which trig function we should use. And that's going to be based off of whatever we find most convenient to avoid having a phase shift. Now, before we decide which trig function to pick, let's try to identify our midline in order to help us determine our pattern. If you recall from our previous sections where we were trying to find the equation for a given graph, what we could do to find our midline is we could take the highest value and drop down by our amplitude, which, since our amplitude doesn't care about the sign of whether we pick A to be positive or negative, we know we would take our maximum value and drop it down 3.8 units. That would be where our midline is located. So here, if we subtract 6.8054 with 3.8, we get approximately 3, which is pretty close to what we see for values in between our maximum and minimum value, which I'll highlight in blue. So if we take a look at our pattern of what I've highlighted, we're starting off at a value of d, which is around 3. Then we go to a plus d, which here we can tell is a maximum. Then continuing the pattern, d, negative a plus d, which is a minimum, and then d again. From this pattern of d, a plus d, d, negative a plus d, and d, we can tell sine is the most convenient function to use here. Now, what should be the sign of a? Should we make it 3.8 or negative 3.8? Well, to figure out which, let's see what happens if we calculate a plus d with the two cases. If we make a the positive 3.8, a plus d would be 3.8 plus 3, which is 6.8. On the other hand, if we make a the negative 3.8, negative 3.8 plus d, which is 3, would be negative 0.8. So looking at the table and the pattern that we see, we know after our first midline point, we go up to a maximum, which occurs at around 6.8, which came from making a the positive 3.8. So here, we'll make a positive 3.8. Now, thanks to our choice of a and sine, and the fact that our pattern starts at our phase shift, we'll have, like before, our phase shift be 0, which means our c is 0, and we don't even have to find b yet. Now we can go ahead and find b. To figure out b, keep in mind our period is the amount of time our cycle lasts, which will be how long it takes to go from a maximum to a maximum value. So here, we can see it takes 10 seconds to go from our first maximum value to our second maximum value, which means 10 equals 2 pi over b, which means b equals pi over 5. Now we have a, b, c, and d. Now we have our model. F of t, which I'm going to use instead of y, equals our choice of a, which was the positive 3.8, our choice of the trig function, sine of pi over 5 t, because t is our independent variable here. We made our c 0 because of our choices, plus d, which is 3. So this function would approximate the data on our table. Now that we have our equation, we can find the period, maximum displacement, and the frequency. Fortunately for our work, we've already figured out the period. Since we know our period, our frequency is just the reciprocal of the period, which would be 0.1. Now, as for the units, since t is measured in seconds, my period is 10 seconds, which means it takes 10 seconds to complete an entire cycle. As for the frequency represents the fact that I complete 1/10 of a cycle in a second. which if you recall from our discussion of the units of frequency, it would be measured in hertz. Last is the maximum displacement. Maximum displacement is another way of saying amplitude, which in this case is the absolute value of A. So whether we pick the positive A or the negative A, we would still get that our maximum displacement is approximately 3.8 units. Now we're going to take a look at some models where some component of our sinusoidal function isn't necessarily constant. Throughout most of our examples, we've been writing our models in the form of y equals a sine of b of x minus c plus d, where a, b, and c, and d were all constant values. However, we may not necessarily need a, b, c, or d to be constant, depending on the context. Our next two examples are going to be very, very similar. For both example 5 and 6, we're going to work with a population of fish that oscillates 10 above or below the average during the year. This oscillation tells us we're going to be dealing with a sinusoidal function. And we're also told it hits its lowest value in January where t equals 0. Now, for the next part, we're told that the average population starts at 100 fish, but what's interesting is that it increases by 100 each year. And we're going to find the equation for our population P in terms of the number of months since January. Now, to start, we're going to first try to identify A, B, C, and D. And as we go, we're going to determine if these values are constant or not. Starting off with A. A is tied into our amplitude. We're told that the population oscillates 10 above or below the average value. So our absolute value of A will equal 10, since the oscillation above or below the average value would represent the maximum displacement or the amplitude, which means A would either be 10 or negative 10. Our choice of our sign is going to depend on which is most convenient to us at the moment. If we take a look at the fact that we start at a low value in January, which is t equals 0. At t equals 0, we're starting with a minimum value. Well, that tells us two things. If we think back to the clock or Ferris wheel problem, the fact that our pattern t equals 0 is starting at a minimum tells us instead of using sine, to avoid having a phase shift, we should use cosine. Also, to avoid having a phase shift, instead of using positive 10 for A, which would mean our start of cosine would actually be A plus D, which would be higher, a maximum, we should use the negative value of A. That way, negative A plus D would be the lower value. So we're going to make A negative 10. So thanks to these two choices of using cosine and making A negative, we'll get C equals 0 because we would have no phase shift. Next, let's figure out B. B is our period. Now, because it says this oscillation is occurring during a year, our period is going to be 1 year, but T is measured in months. So our period, we're going to make 12, which is going to be 2 pi over B, which means B equals pi over 6. So far, thinking about what we figured out B, we made a choice for A, and through that choice of A and our trig function, we were able to figure out a value of C. The only thing we haven't figured out yet is D. What makes D different in this problem is, if you recall from the earlier slides, D is associated with the equilibrium, the rest, or average value of our function. Since the problem tells us that our population average increases by 100 each year, we would associate that with adding 100 every time a year passes. So if we were trying to figure out how much our average population is, we would start off with the 100 fish that we're told we start with, and we would add 100 fish for every year that passes. But remember, T is measured in months. So if we increase the number of fish by 100 per every year, that means our population increases by 100 over 12 per month. So our D would equal 100 plus 100 over 12T. So here D was not constant. Now we can make our function. P of T, our population, would equal our choice of A, negative 10, cosine, our choice of the trig function, times B, which is pi over 6, T. C was 0, plus our equation for D, 100 plus, and we could reduce that 100 over 12, which was 25 over 3. 100 plus 25 over 3T. So our model for the population is P of T equals negative 10 cosine pi over 6T plus 100 plus 25 over 3T. In example 6, we're still going to work with a population of fish that oscillates 10 above or below the average during the year, hitting the lowest value in January where T will equal 0. The average population starts at 100 fish like before, but this time it increases by 10% each month. We're going to find the equation for the population P in terms of the months since January T. This problem is very similar to the last one we just did. The only difference is how our average population increases. If you recall from the previous example, A was negative 10, B was pi over 6, C was 0, and with these choices, that allowed us to work with cosine as opposed to sine. What's different this time is D. This time, we're still starting with 100 fish, but it increases by 10% each month. Well, if you recall from college algebra, that increase by 10% each month is an indicator of an exponential growth. So each month that passes, we would multiply our previous population by 1.1. 1.1 coming from 1 plus the 10%, which is what we would multiply to the previous population. And since we would do that every month, D would have to equal 101 times 1.1 raised to the t power, since we would multiply by 1.1 for each month. So this time, instead of being constant or linear like in the last example, this time our D is exponential. So P of t would equal negative 10 cosine pi over 6t plus 100 times 1.1t. So keep in mind again, D represents the average value of our function. So we do have to read the problem very carefully to determine whether or not our D is actually constant, like we saw in the previous examples, or if it changes, like we've seen here in example 5 or 6. A spring is attached to a ceiling and pulled 8 centimeters down from equilibrium and released. The amplitude decreases by 5% each second. The spring oscillates 10 times per second. We want to find an equation for the distance d. The end of the spring is below equilibrium in terms of seconds t. Now, since we're dealing with a back and forth motion, we should start off with a sinusoidal function. However, we need to be very careful with our different components and our different interpretations of the phrasings we see. For right now, we're going to keep y as our distance. We'll replace it with d later to make sure we don't confuse the d that they want us to use in the problem with the d that we use for the vertical shift or midline. The first thing that stands out is we're told that the amplitude decreases by 5% each second. So this time the amplitude is not constant, which means A is not constant. So if we were to try to calculate the amplitude after t seconds, we know we're starting at 8 centimeters. And since it's decreasing by 5%, that tells us our amplitude could be modeled with an exponential function. Our initial value is 8, and because it's decreasing by 5%, after each second, we would multiply 8 by 0.95, which comes from 1 minus 5%. And we would multiply by 0.95 every second that passes. So if t seconds pass, we would multiply 8 with 0.95 to the t. Now, exponential functions are always positive, but a could be positive or negative. Since the absolute value of a equals 8 times 0.95 to the t, then our two possible values for a are 8 times 0.95 to the t, or negative 8 times 0.95 to the t. I do want to pick the value of a in combination to the function that is going to allow me to avoid a phase shift so I can make c 0. Rereading the problem very carefully, we're trying to find an equation for the distance the end of the spring is below equilibrium. So if we think about our start, we're taking the spring and we're pulling it down. So we're starting 8 centimeters down from equilibrium, which means when t equals 0, our distance, which for right now we're calling y, is 8, not negative 8, because again, distance below equilibrium. From physics, when a spring oscillates, it can never travel beyond where it was stretched and released. So here, at t equals 0, 8 would be our maximum value. Well, if we think about our patterns for sine or cosine, cosine starts at a maximum or a minimum. So instead of sine, we'll use cosine. But what should we use for a? The positive value or the negative value? Our start of our cosine pattern is a plus d. In order for a plus d to be a maximum, a would have to be positive. So a is going to be 8 times 0.95t. And thanks to our choice for the sign of a and our choice of trig functions, that's what allows us to make c 0. Now, as for d being the d in our model to help us with our form of our equation, we're measuring from the distance from equilibrium. More specifically, how far below equilibrium we are. So if I'm at equilibrium, which is where the midline is, that means my distance would be 0, which means d would have to be 0. So now we have a, our choice of trig function, c and d. All that's left is b. In the problem, they tell us the spring oscillates 10 times per second. Well, that would be a frequency. So the frequency would be 10 because 10 full cycles are occurring per second. Well, frequency is the reciprocal of the period. Period, we usually calculate as 2 pi over b. Flip that, and our frequency would be b over 2 pi. Now we can solve for b, and we got b equals 20 pi. Now that we have a, b, c, and d, we can now write our model. So our distance d of t can be modeled by the equation a, which is 8 times 0.95 to the t, cosine, our choice of trig function, of 20 pi t, and thanks to c and d being 0, there is our model. The last example we just did is an example of what we're going to call a harmonic motion. Harmonic motions are back and forth motions that we would associate with pendulums, perhaps the bobbing of a mass that's hanging from a spring. Due to their periodic nature, these motions can easily be modeled using sine or cosine. However, There are different types of harmonic motion. The most basic version of harmonic motion is what we call the simple harmonic motion. This is the type of harmonic motion where the amplitude is constant. The problem with simple harmonic motion is that it's not actually very realistic. The reason why the motion isn't realistic is because of friction. Friction hinders the motion, and as that object begins to swing, it loses energy due to this friction. The more realistic version of simple harmonic motion is dampened harmonic motion. In a dampened harmonic motion, an outside force is causing the motion to slowly stop. We can still model dampened harmonic motions as we've seen in the previous example, but the thing we would have to look out for is that the amplitude or maximum displacement is decreasing over time. Therefore, the A in the model for our sinusoidal functions is not a constant value. It's going to be a function of time. In the dampened harmonic motions, the maximum displacement is going to be an exponential decay function. If you recall from the previous example, our amplitude was an exponential function with a base of 0.95. Since 0.95 was less than 1, that means our amplitude was exponentially decaying. And this exponential decay of the amplitude will result over time in the graph of our sinusoidal function to get closer and closer to 0. As an exercise, take the result from the previous example, plug it into Desmos, and you can see how the wave does not reach the same heights as it does as you look at it from left to right.